So this video follows on from the one on rotational dynamics, looking at how we draw an analogy between mass and moment of inertia. Okay, we've got to grips with the dynamic equations, but all those dynamic equations didn't need to worry about the mass of an object. With these following ones, we do need to worry about the mass of the object, but of course mass, which is what's used in classical mechanics and linear movements, depends just upon a scalar quantity, which is measured in kilograms. However, with rotational dynamics, you need to worry about not just the mass, but also the position of it as well. And so therefore, we have this moment of inertia. In other words, the moment of inertia, which is given the symbol m in kilograms, moment of inertia is given the symbol I, and it's measured in kilograms meters squared. That might give you a hint as to how you work it out. Another way, the moment of inertia is equal to m r squared. However, this is for point-like masses. And different shapes gives rise to different ratios. Give different ratios. Let me give you some examples. Let's imagine this is our axis of rotation, and we have this hoop attached to it. A rather large hoop, like a wheel with spokes on it. It's obviously rotating around the axis. And the moment of inertia in this instance is very simply mr squared. It's quite straightforward, assuming that these are massless, and all the mass is around the outside of the rim. Just try and draw that. However, if we used another shape, which was a cylinder, a solid cylinder, and that was rotating, then the moment of inertia here is actually a half the total mass times r squared, where r is the radius from each of those. So differing shapes will give differing moments of inertia, but they'll always be stated, always given in problems. However, what they might do is they might give you a moment of inertia and then say a mass of sorts is going to be deposited somewhere. What is the new moment of inertia? So, but you will have to add extra masses to known moments of inertia. For instance, I new is going to be I old plus the moment of inertia that you're calculating. And you might then have to use the new moment of inertia in a calculation. Right, okay then, so I think, if we can now assume that the mass and moment of inertia are the equivalents between linear and rotational motion, then this gives rise to the very useful idea that also, just put this on the next page, that the reason why mass came up, that's a bit tough. I was going to say the reason why mass came about, but Newton's second law implied that if you put a force, a resultant force on an object, then there would be a resulting acceleration. And the constant proportionality of that is the mass of the object. I wouldn't say how that mass arose, but that's a really good way of thinking about mass. Mass is the resistance of an object to accelerate when a force is put on it. If the mass is very high, for a constant force, the acceleration is low, and vice versa. Now, once again, there is an equivalent idea of this, which deals with rotational mechanics, and that talks about the force applied to an object is proportional to the angular acceleration, which we know is alpha. And obviously the constant proportionality is the moment of inertia. However, I've left this big gap here because when you're dealing with an object which is rotating and you're applying a force to it, here's the axis of rotation. Not only does it depend upon the size of the force that you're applying to it, but also how far that force is being applied away from the axis. The product of force times the distance is known as the torque, which is given the symbol T, which is Newton meters, its units. So therefore, what I should say back up here is the force times the radius, how far away the force is being applied, is proportional to the angular acceleration. Therefore, force times radius is equal to the constant proportionality now is the moment of inertia times alpha, or finally, torque equals moment of inertia times angular acceleration. And this is Newton's second law, rotational equivalence to F equals ma. Torque is measured in Newton meters, moment of inertia is measured in kilogram meters squared, angular acceleration alpha is measured in radians per second squared, and that shows you the dimension check holds up. Good, okay then, so really what we're doing is we're going to now look at those two ideas, moment of inertia and the Newton's second law equivalent in terms of torque and moment of inertia. In other words, for the same torque, if you have a larger moment of inertia, the angular acceleration is less. Okay, so let's go straight into an example. Let's have a flywheel. You'll notice that flywheels are used quite a lot. Let's say a force is being applied which is 5 newtons at 15 millimeters from the axis. It's being applied for 10 seconds and the moment of inertia is 1.2 kilogram meters squared. Okay, a few questions here. First one is, what is the angular acceleration? The second one is, what is omega after 10 seconds? Okay, if you think you know, hit pause, otherwise here comes the answer. Okay, first of all, I suppose part 1, if you like. That's part 2. Part 1 says, what is alpha? So let's go to our equation. Torque is moment of inertia times angular acceleration. Angular acceleration is therefore the torque divided by the moment of inertia. The torque, straightforward, is force times radius. I'll write that in again just to make absolutely sure we're happy with it. So therefore, 5 times 15 millimeters, let's convert that into meters, and divide it by 1.2 kilogram meters per second, giving us 0.0625 rads per second squared. Okay, part 2, what is omega after 10 seconds? Well, it's whatever the initial angular speed is, plus angular acceleration times by time period. We know that's 0 initially, so therefore it gives us simply alpha t, which is 0.0625 0.625 multiplied by the 10 seconds, giving us 0.625 rad seconds. Hopefully straightforward. Okay, let's go for another one. Let's go for a centrifuge this time. Let's imagine our centrifuge is spinning around with test tubes. We'll do as many as we want. And let's say that we have a working speed of 1,100 rads per second. And it achieves this in 42 seconds. The moment of inertia around the axis is 7.6 times 10 to the minus 4 kilogram meters squared. It obviously looks very small. These are test tubes after all. And the question is, what is alpha? And what is the torque required? Okay, 1 and 2. The torque required to achieve that speed in that time. Okay, if you think you know the answer, hit pause. Here comes the answer. Okay, first of all, alpha. What is alpha? Well, alpha is going to be the change in the angular speed divided by the change in time, and we're looking for 1,100 rads from 0 in 42 seconds. And that gives us 260 rads per second. It's going to go through 260 radians each second. Okay, point 2. What is the torque required? Well, we know that the torque is going to be moment of inertia times the angular acceleration. All the information here is given for us to simply substitute using our previous answer, which gives us 0.2 Newton meters. Good. Now, what's going to happen now, and this is likely to happen in the real exam papers, it will say that now you introduce liquid to the test tubes. Which have a total weight of, mass, of 2.4 times 10 to the minus 3 kilograms. And it's at a radius of, their centre of masses are at a distance of 84 millimeters. Okay. In other words, now we have, like, we've filled these up. So their moment of inertia has subsequently changed. Okay, now with the same torque, how long to achieve the working speed? Of 1,100 radian seconds. Right, if you think you don't know the answer, hit pause, otherwise here comes the real answer. Okay then, so what happens here is, well, very straightforwardly, we know that the new moment of inertia is the old moment of inertia plus mr squared, mass times radius squared. It's it's simple. It's not a shape of an object, so we can simply have mr squared here. That gives us 7.6 times 10 to the minus 4 plus 2.4 times 10 to the minus 3 by 84 millimeters, let's convert it to meters, squared. And that gives us a value of, just type this into the calculator, 7.6 7.76 times 10 to the minus 4 kilogram meter squared. Very little change, but nonetheless a change has happened. Now, we need to work out, therefore, the new angular acceleration, which is torque divided by the new moment of inertia. The torque is the same, 0.2. Divide that by the 7.7. Gives us our new moment of inertia, which is 257.4 rads per second squared. Now, the time, well, let's write out the equation first. The final angular speed is the initial angular speed plus alpha t. You know this is 0 because it's starting from rest. Therefore, t is going to be the final speed divided by the final angular speed divided by the angular acceleration, which is going to be 1100 divided by 254.4, gives us 4.3 seconds, which is not quite right. Just have a quick look at that again. Yep, I think that's right. Well, if you can find an answer, if you can find an error with that, I'd be keen to hear about it. But pretty much we've taken the old, we've added it to the new. Yep, that's right, and so it comes out as 3.4. Sorry, 4.3 seconds. Good, okay then. I think that's it. Just bear in mind, of course, the equivalence of Newton's second law. That makes life very easy to, you can start to picture what's happening and anticipate they're likely to ask you to add something to get a new moment of inertia from an old. Okay, next time we'll deal with rotational kinetic energy.